Welcome to MEI Mechanics. We're on the topic Centre of Mass, and this is video 1.1, Introduction to Centre of Mass. Now, in a normal object, the mass of that object will be spread out around the object. So when we talk about the centre of mass, we are thinking about all of that mass acting as if it's at a single point. It's kind of an average position of all the mass that's within the object. And often we can correctly model an object in that way, as long as the object's not under any forces which are going to make it rotate, then it does behave as if it is a single point at the centre of mass. Now we use the symbol x bar to denote the centre of mass, and often if we've got a simple situation like a uniform rod, by uniform we mean that the mass is evenly distributed throughout the object, then the centre of mass will be at the geometric centre of that shape. Things become more complicated if the mass is not uniformly spread, or if there are individual masses within the object which we can identify, in which case it won't be at the geometric centre. Now, in order to define the centre of mass and to calculate the centre of mass, we think about moments. Now, the word moment in mechanics and science in general refers essentially to anything where you've multiplied something by a distance or by a position. So in this case we're talking about a mass times a position, and what we find is that the moment of the total mass of the object, so we'll write that as big M, multiplied by the position of the centre of mass, is equal to the sum of the moments of all the individual masses that make up the object. Alright, so that total mass of course is the sum of those individual masses, so sometimes you'll see this written with a big M, or sometimes you'll see the sum of those M's on the denominator with x bar on the left. So this is the standard calculational tool that we're going to use in order to calculate the position of a centre of mass. So let's have a look at an example then. Now before we can do any centre of mass calculation, we need to decide where we're going to use as our reference point in order to say where the centre of mass is. If we're going to treat this rod as a one-dimensional object, then we can put our reference point here. Alright, so that's like our origin. And so then what we're going to do is we're going to look at these three individual masses and decide where their individual centres of mass are and the moments of those individual objects. Now because these things are uniform, then the centre of mass of these are going to be at their geometric centre. So for this piece here, because it's 20 centimetres long, it will be 10 centimetres from the origin. This piece here will be the whole of this 20 centimetre distance plus another 10, so that will be 30, and this one will be 50 centimetres away from that origin. Alright, so the centre of mass, remember I get that by multiplying the mass of each object by its distance from the origin, or its displacement technically from the origin. So that will be 0.04 times 10, working in units of kilograms and centimetres here, that's fine, we'll just stay consistent with that, means our answer will be in centimetres, plus 0.03 times 30, because remember we decided that that whole distance there from the origin to there was 30, and then plus 0.02 times 50, and then that's all divided by the sum of the masses. So that's 0.04 plus 0.03 plus 0.02. And that works out as 25.6 centimetres. So the centre of mass of this whole object is 25.6 centimeters to the right of this origin. One way of thinking about the centre of mass, we mentioned it's a type of average earlier. This really is like a mean average, except that it's weighted. Alright, so if all of these objects had a mass of 1, then this would be the same calculation that we would use to find the average position. Alright, because the thing we'd be dividing by would be the sum of those 1s, so it would be the number of things. Alright, so these, so the masses are the weightings that we're giving to each number when we're calculating this weighted average. Now, in this example, we're dealing with a slightly different situation. This rod is described as light. Now, in the language of mechanics, that means that we're going to treat it as if the rod itself has no mass. But there are individual point masses attached to that rod at various places. So again, we can do a similar type of calculation. We've got an origin here, and we're just going to try and find the coordinates of the centre of mass. But we're going to do it in a slightly different way this time. We don't have to, but this will set the scene for later, a nice way of setting out the work. And we're going to actually use a table this time. So we need column headings for the individual masses, for their positions, and for the product of the mass times the position. This is actually going to be a very similar calculation in the end to what you do when you do means and frequency tables, if that helps you to think about what's happening here. So for this first mass is 2. Position, well, we're not given any units, but we'll just work in whichever units these are. These, we're looking at the x coordinates here, so the x coordinate there is 1, and mass times the x coordinate, 2 times 1, is equal to 2. Then for this mass, that's mass is 3, position is 3, 3 times 3 is 9, and for that third mass we have a mass of 5, position of 8, 5 times 8 is 40. Now remember, for our calculation we're going to be doing the sum of the masses times the positions divided by the sum of the masses, so we can add up those two columns. The masses, you can see there, add up to 10. And if we add those numbers up for the mass times the position, they make 51. Alright, and if you remember from our formula, it's the sum of the m times the x's divided by the sum of the m's. So the position of the centre of mass is 51 divided by 10. So that's 5.1. Now we're working here with coordinates, setting the scene for the two-dimensional work we're going to do later. So if I then want to say where the centre of mass is, often shortened to COM, that has position 5.10. So we're now going to move into the two-dimensional world and think about how we can find the centre of mass in that case. So in this case we're going to need a pair of coordinates to define the position of the centre of mass, and just like in the examples that we've seen, we also need to define an origin and a set of axes. Now you have a complete choice as to where you put your origin, and then as long as you state your centre of mass correctly relative to that origin, then you'll be correct. Unless you have a good reason not to, I would suggest always putting the origin at the bottom left of the shape that you're looking at. So if we were going to try to calculate the centre of mass of this shape, I would put the origin here, that would be my x-axis, and then going vertically up from there, I would have my y-axis like that. Alright, and then I would try to calculate, using whatever methods were available to me, where the centre of mass of that shape was, and I would express that centre of mass using this coordinate system. Now the calculation in 2 dimensions is no different really from 1 dimension. We just do the same thing in the y direction as we've already been used to doing in the x direction. So that's nice, very simple. And here's an example. So we have 4 individual masses here, A, B, C and D. and we're going to try to calculate the position of the center of mass of those four objects combined. Alright, now we're given a coordinate system there to work with, so we'll work with those coordinates, and here we have a table that we can use to do our calculation. Just like the table we saw earlier, except that there are two columns, one for x and one for y here, and therefore two columns for the products as well. Alright, so let's do these in order. We'll start with A. These have masses 6, 3, 3 and 2 kilograms respectively, so A has mass of 6, so we'll record that in there. The x coordinate of A is 4, the y coordinate is 1, and then I'm going to multiply each of those coordinates by the mass, which is 6, so we'll get 24 and 6, like that. Alright, keep going in that manner, and we end up with this table of values here. Notice, of course, for objects like D and C, they have at least one negative coordinate, so we've got to make sure we use a negative number there. And then, just like before, we add up the masses, add up the product of x times the mass, and because it's two-dimensional, we're also adding up the product of y times the mass, and then we're doing a separate calculation for x and for y. So for x, we are doing x bar is 48 over 14, and y bar is 8 over 14. Alright, so they work out as 3.4 and 0.6, so the centre of mass is that coordinates 3.4, 0.6. So why don't we plot that on our graph, and we'll see if we can make sense of it. So 3.4 will be there, 0.6 takes us up to there, so that point there is the centre of mass. Alright, now notice it's in the middle of all the objects, but because there are 3 objects over this side and just 1 over there, that's pulled that centre of mass way over to the right. Alright, so the centre of mass is trying to be as close to all of the mass as it can be. So the more mass you have on one side of an object, the further to that side the centre of mass will be. So that concludes video 1.1, Introduction to Centres of Mass. In the next video 1.2, we're going to look at the centre of mass of laminas.